So here we'll show that the rotation matrix has an eigenvalue of 1. So suppose this is the rotation matrix and the elements are this. So it's the first row, second row and third row, and we know rotation matrix is an orthogonal matrix, so R transpose R is equal to 1, or the transpose is the inverse. So if this is this, then this is the transpose of this. So the first row has become the first column, the second row has become the second column, and the third row has become the third column. This into this is R transpose into R is equal to identity matrix, so this one. So now let us form a vector n1 from the first column. Similarly, n2 is a vector formed from the second column, and n3 is a vector formed from the third column. So if you multiply the first row with the first column, you get n1 dot n1, that is a11 square plus a21 square plus a31 square, and that is equal to 1. Similarly, n1 dot n2, if you do n1 dot n2, that has to be 0. n1 dot n1 has to be 1, and n1 dot n2 has to be 0. So n1 dot n2 is a11, n1 dot n2 is here, a11 a12, so a11 a12 plus a21 a22 plus a31 a32, and that has to be 0. Now if you see, if you take the dot product n2 dot n2, again you get 1, and n3 dot n3 you get 1. So this shows that n1, n2, n3 are unit vectors and they are mutually perpendicular. So each column of the rotation matrix can be considered as coefficients of mutually perpendicular unit vectors. So again you can show that n1 cross n2 is equal to n3. That is, n1, if n1 is formed from this and n2 is formed from this, then n1 cross n2 is n3, n2 cross n3 is n1, and n3 cross n1 is n2 in cyclic order. So this we can verify using this symbolic computation code segment. So suppose we start from here. So in the last lecture we have seen how to get the rotation matrix from the transformation matrices. This we did in our last class, and in this code we have imported one new library, that is SymPy vector. So from sympy.vector import star. So why we have imported this vector, that you will see a little later. So if you run this, okay, so let us clear this space. Now this is the rotation matrix. Now so let us form a coordinate system. So this is a class and C is an object which is instance of this class coord_sys 3D, and this is the name of the class C. So now we can form the vector n1 as this R 0 0, that is first row first column into C dot I plus R R1 dot 0, that is second row first column into C dot J plus R now third row first column to C dot K. So this is the vector n1 as we have seen here. This is n1. n1 into n3. So this is n1 and let us copy this line and paste it here. So n2 is R, so this becomes the second column, and then we copy this and paste it here. So this becomes the third column. So now the three vectors are formed. n1, n2, n3, these three vectors are formed. So if you run this, so now dot n1, so you get an expression like this, but you expect a value of 1. So you just simplify using this trig simp. So this is 1, and if you expect a 0 value here, and yes, you are getting 0. You are expecting a 0 value again, and yes, you are getting it here. Now what about n1 cross n2? So cross n1 n2 and you get this. So what value do you expect here? That n1 cross n2 should be equal to n3, because this is the property of this rotation matrix, and see, this n3 is actually n1 cross n2. So this rotation matrix is a general rotation matrix formed from 3 consecutive rotations, and the rotations are the Euler angles. So in this general rotation matrix, you can show that n1 cross n2 equal to n3, n2 cross n3 equal to n1, and n3 cross n1 equal to n2 in cyclic order, and you can verify it using this symbolic computation code segment. It is difficult to do by hand calculations. So now we come back to our write-up, where so n1 cross n2 equal to n3, n2 cross n3 equal to n1, and n3 cross n1 equal to n2. So you refer to the SymPy code segment. Now from n1 equal to n2 cross n3, if you actually perform the cross product, so this is n1 and this is n2 cross n3, so this is n1, this is n2 cross n3, so this is the cross product. So now equate the coefficients, and a11 is this, so a11 is this, and a11 is nothing but the cofactor of a11. So the cofactor of a11. Similarly, you can show that a22 is cofactor of a22 and a33 is cofactor of a33. So cofactor of A22 is A22 itself, and cofactor of A33 is A33 itself. So this is a property of the rotation matrix. Now what do we get out of this? Here you see we are interested in finding out the eigenvalue of the rotation matrix. That means this. So this. That means now the determinant of this has to be 0. So what is the determinant of this? We know the determinant of this is this, and determinant of R is 1. Rotation matrix, the determinant of rotation matrix is 1, and cofactor of A11 is A11 itself, cofactor of A22 is A22 itself, and cofactor of A33 is A33 itself. So this simplifies the thing. So this one and this lambda cube forms this first term. Then you this A11 plus A22 plus A33 you take common, and that is lambda square minus lambda. So lambda into lambda minus 1. So minus 1 minus lambda, and from this lambda square plus lambda plus 1, and from this minus A11 plus A22 plus A33 into lambda. So from here itself you see lambda equal to 1 is an eigenvalue. So this itself shows that lambda equal to 1 is an eigenvalue of the rotation matrix. And if you take this this term as, so you take lambda square, then minus lambda, you include this as minus 1 and this, and plus 1, this plus 1 here, and you take this group of terms as 2 cos phi, then this becomes lambda square minus 2 cos phi lambda plus 1, and the other two eigenvalues are this, that means cos phi plus minus j sin phi, or e to the power plus minus j phi. So these are the three eigenvalues of the rotation matrix. So let us stop here.